give a big, warm, build stuff welcome, Kim Maida.
Thank you. The screen is so cool. So I'm here to talk to you about the art of authentication for web apps. Now let's say it's your first time adding authorization and authentication to an application. I really liked this tweet from Nick Craver from a few years ago because I think it embodies a lot of the experience many people have. So it says, step 1, are you ready to work on the auth code? Step 2, new dev says, hell yeah, bring it on. And then the lived experience often ends up looking something a little bit more like this. Now, the problem that many people have with authentication and authorization is that they go on the internet and they search for authentication, and then they're basically told by a lot of the resources that are available that step 2 is just do the rest of the freaking auth stuff. And the rest of the authentication and authorization concepts, the specifications, the technical details, these things just kind of continue to remain a mystery to people when they try to do this. There's a reason for this, though. You don't actually need to know everything in between these two steps to have safe, secure, effective auth. If you use an identity as a service platform like Okta or Auth0 or Ping, or database auth offerings like Firebase Auth or Supabase Auth, these things can provide you with standards-based authentication and authorization without costing you and your organization hundreds and hundreds of development hours to engineer all of this stuff yourself. But I'm assuming that's not why you came to this talk. You didn't come here for me to say and just draw the rest of the owl. You're here because you want to know how to draw the owl. So what I'm going to do is I'm going to go into the foundational concepts behind authorization and authentication. And like I said, though, you don't need to be an expert in all of this to get to a good end result. But what I'm going to do is try to pull back the curtains for you a little bit today. So I'm going to start with an introduction to commonly used open standards. I'm going to go through this in what's hopefully an approachable way and provide you with a foundational knowledge on standards-based authorization and authentication. And in order to do that, we have to start by covering some terminology. So let's begin with digital identity. Now, digital identity refers to a set of attributes that define an individual user in the context of the function being delivered by a particular application. So for example, let's say that you're an online shoe retailer. The digital identity of your users might consist of something like their credit card number, their shipping address, and maybe their purchase history. Next, there's authentication. Now, authentication refers to the process of verifying that the user is who they say that they are. On the other hand, we also have authorization. And authorization is really about granting or denying access, rights to access resources. So let me give you a metaphor. Let's say that you're going to travel by plane. When you get to the airport, you authenticate at security by presenting your ID or your passport. This is you proving that you are who you say that you are. Then when you go to board the actual plane, you present your boarding pass as authorization. This grants you access to get on the airplane. Now, if we return to the world of applications, the concept of authorization brings us to the OAuth specification. Now, fortunately for us, OAuth standards are really clearly defined. However, also kind of unfortunately for us, they're very dense and they can be difficult to grok. So the first thing I want to do for you is demystify OAuth. And in order to do that, we kind of have to start out with covering why OAuth was created in the first place. What problems does it exist to solve? So before OAuth 1.0 was created in December of 2007, if we wanted our application to access third-party resources from another party, it looked something like this. Let's say that you're a user, and you use a web app called Hire Me. This is an app that you can use to search for and apply for jobs, and then also to schedule interviews. Now let's say you also use a web app called MyCal to manage your personal calendar. And now maybe you've used HireMe to schedule a job interview and you want to be able to allow HireMe to add an event to your MyCal. Before OAuth, this is what would happen. HireMe would ask you, the user, for your MyCal credentials. You would give your MyCal username and password to HireMe, and HireMe can then call the MyCal API to do things like create calendar events on your MyCal on your behalf. And it does this by using access that was provided by sharing your MyCal username and password with HireMe. Now, I hope that you can see immediately that this is bad, right? This approach relied on sharing a user's personal login information from one application with a completely different app. In a general sense, this is pretty much a terrible idea. If HireMe doesn't do their due diligence to protect your MyCal credentials, well, they really have a lot less at stake if there's a data breach and those credentials get shared publicly. That's disastrous for MyCal, on the other hand. And also, the other problem is that HireMe just has way too much access to the MyCal API. Because you've given it your access, HireMe can now do anything that you can do in MyCal. That means it could delete events, or change your settings, or access your phone number, or even your payment info. So this is why OAuth was invented, to give us a better way here. In this talk, I'm specifically going to discuss OAuth 2.0, which is an open standard for performing what we call delegated authorization. Now, using OAuth, MyCal can delegate some authorization to HireMe in order to grant it limited access to the MyCal API, but without incurring all of the risks that I just talked about. And the way it does this is using something called an authorization server. An authorization server is really just kind of a fancy word for a set of endpoints whose purpose is to interact with the user and to issue tokens in order to perform delegated authorization. And delegated authorization allows a party that holds some authorization to delegate a subset of that authorization to another party without requiring either party to disclose any user credentials to the other. So what does this actually look like? Well, we have HireMe and we have MyCal, and now we're going to use OAuth 2. This means that MyCal now has an authorization server, this set of endpoints. And we're going to assume, for the sake of example, that HireMe has already registered as a known client with MyCal. That basically just means that MyCal is aware that HireMe as an entity might be asking it to delegate authorization. Let's say that you, as a user, are logged in with HireMe already, and HireMe wants to set a calendar event on your MyCal for that interview that you've scheduled. The first thing that happens is the browser performs a GET to send an authorization request to the MyCal authorization server. The MyCal authorization server is then going to prompt you, the user, to log in with MyCal if you're not already logged in. So you're going to give your user credentials to MyCal for MyCal. And at this point, the MyCal authorization server is going to prompt the user in the browser for their consent to allow HireMe to access the MyCal API to add an event on the user's behalf, but not do more than that, just add an event. You then have to explicitly agree to this. So if you agree, then the MyCal authorization server will send an authorization code to HireMe in the browser. HireMe takes that code and it takes its own app credentials and it sends those back to the MyCal authorization server server-side. At this point, if everything checks out, then MyCal can issue an access token, which HireMe can use to call the MyCal API. But it can only do this within the scope of the permissions that were accepted by the user. So HireMe can now set calendar events for the user with the MyCal API, but not do more than that. So this is great, right? Nothing insidious is happening now. MyCal is asking the user to log in with MyCal. HireMe is not asking for your MyCal credentials. HireMe can only create events, not read all of your events or change any of your settings. And the issues that we have with sharing credentials and really just HireMe having way too much access to the API, these things are no longer a problem. But then everybody loved OAuth 2 so much that companies and organizations wanted to do more than just call APIs. They wanted to be able to sign users in with accounts that lived in other systems. For example, maybe HireMe wants a MyCal user to be able to log into HireMe using their MyCal account, even if they don't have a HireMe account explicitly. The thing is, OAuth 2 is for delegated access. It is not intended for authentication. This means that if HireMe does something like use the access token that it was given by the MyCal API, and just assume that by having this access token and calling the API successfully, it means that the user can be considered authenticated with HireMe, we start to run into problems. Access tokens are for the API. They're meant to be opaque to the client. Therefore, somebody could have stolen this token. The token could be for a completely different user, or it could have even been obtained for a different client that's not HireMe and then injected into HireMe. And we call this the confused deputy problem. HireMe doesn't know where this token came from, nor do they know who it was issued for. And if you recall, authentication is about verifying that the user is who they say that they are. And HireMe just can't know this from the fact that it can use this access token to get resources from an API. Access tokens are for authorization. However, this didn't stop companies from co-opting this process for authentication anyway. And as expected, they had problems with it. So it became clear to the security community that we needed to address this. And to do that, we needed to formalize authentication on top of OAuth. And as everybody knows, we did this. Modern apps do this all the time. You can log in with Google, Twitter, Facebook, so on and so forth. So clearly this problem has been solved. And it was solved by the creation of a new specification called OpenID Connect, or OIDC. Remember, OAuth 2.0 is for delegated authorization. OpenID Connect is for authentication. And it's easy to get these concepts and these specifications confused with each other, especially because their flows and their details are built on the same foundation. So OpenID Connect is an identity layer on top of OAuth 2 for authenticating users with an authorization server. In both specifications, the role of the authorization server is to issue tokens. So let's talk a little bit more about tokens. And for authentication with OIDC, we use ID tokens. Our authorization server can issue ID tokens similarly to access tokens, which I discussed briefly in the first example with HireMe and MyCal. However, unlike access tokens, ID tokens are intended for the client. ID tokens are a fixed format that clients can parse and validate in order to extract identity information from the token and therefore authenticate the user or verify that the user is who they say that they are. Now, OAuth 2 describes how access tokens are issued and managed, and OpenID Connect extends OAuth 2 to show how to issue ID tokens. The OIDC spec declares a fixed format for ID tokens, and that format is the JSON Web Token format. So I'm going to dig into JSON Web Tokens a little bit, what they contain, and why this format is useful. A JSON Web Token typically looks something like this. It's also often abbreviated as JWT, which some people pronounce as JOT. I guess it's easier to say. But it's 3 string segments concatenated with periods. The first segment is called the header segment. This is a JSON object that contains the signing algorithm and the token type, which in this case is always going to be JWT. This JSON object is then base64 URL encoded, which makes it URL and file name safe. And then the second segment is called the payload segment. Now these are claims. This is a JSON object containing statements about the user, identifying the user, and also statements about the authentication event itself. Again, this is base64 URL encoded. And then the final segment is the crypto segment, or the signature. Now, JSON Web Tokens are signed so that they can't be modified in transit. I'm going to talk about the RS-256 signature here, which, if you recall, was the algorithm that was listed in the header segment as being the algorithm used. And RS-256 is a known entity. So knowing which algorithm to use enables us to validate the signature. And I'm going to peek into the contents of the black box a little bit here. This information is actually kind of hard to find in a general sense if you're trying to figure out how JSON Web Tokens are signed and validated. And I want to go through how the signature is created to show why and how it gives us confidence that the token can be used and is trustworthy. So what happens in the signature is we take the first two segments of the JSON Web Token. These are the base 64 URL encoded header and the payload. And these two segments together are called the signing input. We know that the signature algorithm is RS-256, so this means that we're going to use the SHA-256 hash function to hash this signing input. Now, hashing is irreversible. So a hash function means that you can take the same input, put it through the function, and you'll always get the same output. And no two different inputs will ever produce the same output, but once you've got that hashed output, there's no way to get back to the original input. Now, RS-256 is an asymmetric signing algorithm. We are going to encrypt the hash header and payload using a private key. Now, unlike a hashing, encryption is reversible. So we can decrypt the result with another public key to get back to the original input. Now, only the token issuer, in this case the authorization server, has access to the private key, so only the authorization server has the ability to mint and sign tokens to create the signature in the first place. Then what happens is when the client receives the JSON Web Token, the client is going to validate the signature using a key. And in this case, because we're talking about asymmetric signing, different keys are used to sign and validate, and the public key is going to be used to validate. So how does the signature actually ensure that the token wasn't modified in transit? Well, in order to validate the signature, the client is going to take the header and the payload from the token that it received. And since it knows the algorithm, it's going to use the SHA-256 hash function to hash these two segments. This is done on the client side. This is the same step that the authorization server already performed in order to create the signature in the first place, right? What this does is it gives us the same hash that the authorization server then encrypted in order to create the signature. So then the clients can decrypt the signature using the public key. And this gives us the signature hash that the authorization server created. We can then compare the hash that was just computed on the client side with the decrypted signature hash from the token's crypto segment from the authorization server. And if these two things match, then the token signature is validated. And this tells us that nothing in the header or payload has been changed between the time that the token was issued by the authorization server and when it was received by the client. Now, validation of the signature is something that we typically wouldn't do manually in our applications. Instead, we would use a JSON Web Token library or an identity services client SDK to do this. So now that we have our validated ID token data, we can take a look at what's in it. And I mentioned that the payload segment contains useful data. This is a JSON object with claims that contain statements about the end user and the authentication event. So I'm going to talk about these authentication claims first. They might look something like this. First, you have your issuer. This is the authorization server that issued the token in the first place. Then you have your audience. This is the unique ID of the application that the token has been issued for. We also have timestamps. These tell us when the token expires and when it was issued. And then we have something called a nonce. And a nonce is a cryptographically random string that binds the client to the ID token that it receives. What happens is the client generates a nonce, and then it sends it with the auth request to the authorization server. The authorization server then includes that nonce from the request and it puts it inside the token that it issues back. Then when the client decodes the token, we need to check to verify that the nonce that's contained in the token is the same nonce that we sent with the authorization request. This is done to protect against what we call token injection, or tokens that are coming from somewhere other than the authorization server, or tokens that are actually affiliated with a different authorization request and could be for a different user. So in addition to validating the signature, clients also need to verify the authentication claims that exist inside the token, like the issuer, the audience, the timestamps, and the nonce. And once we've done that, we can use and trust the token contents and verify that the user is who they say they are. So that kind of brings us to the meat and potatoes of the ID token, right? That's the actual identifying information. And some standard claims that we can ask our authorization server to include are things like the subject. This is the unique user identifier. And then various other profile information. These are things like address, nickname, photo, email, so on and so forth. Okay, so now that the user is authenticated, that means we're ready to call a resource API. So I'm going to cover access tokens in a little bit more depth than I did before. Now, access tokens are for accessing resources. As we saw with the MyCal API, it would grant access to that API. Unlike ID tokens, which are JSON Web Tokens as per the OIDC specification, access tokens have no specific defined format, and they don't have to be and are not necessarily JSON Web Tokens. However, many authorization servers do use the JSON Web Token format for access tokens. This includes companies like Auth0, Amazon Cognito, Microsoft Identity Server, Okta, and others. And the reason they do this is because the format enables validation, as we saw. Now, access tokens are intended to be received by a resource API. Unlike ID tokens, they're opaque to the client. The content in an access token could change at any time. And because they grant access to a third party, they should have a short expiration time. They need to be short-lived. Resource access throughout the user's session may also change, which means new access tokens will have to be generated during that time. So the client should never contain any code that relies on content in the access token, because they're for the resource API. So what does API access with an access token look like? Let's say we have our user and they're logged into the client application. And then we have our authorization server. And we're going to request an access token to get resources from an API. When a call to the API is made to request data, we attach the access token to the request, and we send that request to the API. The API then uses middleware to validate the access token. And if everything checks out, then data can be sent back to the application. But this kind of leaves a fairly significant question. When we're delegating authorization, how does the API know what level of access it should give to that application that asks for resources? Well, we do this with something called scopes. Remember this? We only want HireMe to create calendar events with the MyCal API, but not do more. So scopes limit what an application can do on the behalf of a user. They can't grant privileges that the user doesn't already have. So if a MyCal user doesn't have the privilege to set up, let's say, new MyCal enterprise accounts, for example, then any scopes granted to HireMe as an application allowing users to set up enterprise accounts won't supersede the user's actual permissions. So that means even if the application has a scope to create enterprise accounts, if the user can't do that on the API, then they won't be able to do this. Scopes delegate access control to the API or the resource. This means that the API is the one that's responsible for combining incoming scopes with what it knows about actual user privileges, and then it's going to make the appropriate access control decisions as a result. So if we have a user using an application, maybe it's HireMe, and we want to access the third-party MyCal API, let's say that we've already acquired an access token from the authorization server. And the token that we received from the authorization server already contains the user identifier, the audience saying that the token was issued for hire me as a specific client, and a scope for permission to write calendar events. When we send this request to the API, we have this write events permission, but this API can access the calendar of hundreds of thousands, if not millions, of different users. So in addition to looking at the token scope, the resource API needs to use the subject identifier to only allow this user to exercise their own capabilities on their own account and not modify any other user's calendars. So in the context of delegated authorization, scopes express what an application can do on the user's behalf. They are a subset of the user's total capabilities. So remember when we prompted the user for their consent in the browser for MyCal to allow hire me to do certain things? Well, more realistically, this consent dialog might look something like this. And I'm sure you've seen things like this when you sign in with Google or something. It asks you to allow certain permissions. So hire me could ask for a variety of different scopes in this case, but you shouldn't overload scopes with user-specific permissions because scopes are intended for app-level permissions. So what have we learned so far? Well, we've taken the concept of going from a vague idea to a much more complete solution and filled in some of the concepts and the background in the middle, including OAuth 2, OpenID Connect, authorization servers, ID tokens and the JSON Web Token format, access tokens, and scopes and delegated authorization. So next, what I want to talk about is the implementation of authentication in web applications. But first, this is a pretty dense talk, so we're going to take just a little bit of a break. My name is Maida. I'm the Vice President of Developer Relations at Cloudinary. I'm a Google developer expert in security, privacy, payments, and identity, and an Auth 0 ambassador. As a hobby and a side gig, I make realistic miniature food, charms and jewelry, and dioramas. And I also sculpt and resin cast artisan keycaps for mechanical keyboards. Finally, I draw and design custom vinyl stickers, which I then take with me to conferences that I speak at in order to give away to people for free. I especially like designing holographic stickers, so definitely come talk to me after the talk if you want to talk about Auth or if you just want some free stickers. Okay, so if we come back to the main topic, let's talk about authentication for web apps and how we implement login with different web application architectures. First, I'm going to talk about authentication in what we sort of refer to as traditional web apps. These are server-side web applications. For example, apps built in PHP or .NET or Java. So in this case, we have our browser. And then we have our server, and on the server we have our back-end code running a web application that presumably has an API and access to data, so a database. And then we have an authorization server. So using the browser, the user authenticates by providing their credentials, and an authorization request is then sent to the authorization server's authorization endpoint. The authorization server issues a code and redirects the user back to the application with the code. The application then takes this code that it received, it takes its own client ID and its client secret, and sends them to the authorization server's token endpoint. All of these things are verified by the authorization server, and if everything looks good, then the authorization server issues tokens, which are stored securely in the server-side application. The server then sets a cookie in the browser, and this cookie represents the user's session. At this point, the user is considered authenticated, and they have access to data. Then on any subsequent requests for pages, or whenever there's traffic to this domain, that cookie is attached by the browser and sent to the server. The application then gets sensitive data from the API using the API token. And the requested page HTML and any sensitive data is sent back up to the user in the browser. Now, if the cookie is expired, or if there is no cookie and a request is made for protected data, then a 302 redirect status is returned. At that point, the browser will do a full page redirect so that the user can re-authenticate. Once they're logged in again, then we can send secure data to the user in the browser once more. But let's also talk about single-page applications built with JavaScript. We're in an era where JavaScript is essentially eating the world of web development, and we have special security needs for JavaScript applications. These apps are often secured using tokens, and I'm going to cover an overview of the general architecture, and then I'll get into the details in a little bit. So at a high level, it looks like this. We have our browser. And then when a user navigates to the application, the app is compiled, downloaded, and runs within the browser itself. Then we have an API, which provides data resources to the single-page application. And we have an authorization server. When the user wants to log in, we make an authorization request to the authorization server. The credentials for the user are verified, and then tokens are issued. And this could be either just an ID token, or it could be both ID and access tokens if we need resource access to. The tokens are sent to the single-page application that's running in the browser. And the authorization server has the ability to set a cookie in the browser for the authorization server's domain. This represents the user's session with the authorization server. In the client, the ID token is parsed, and then it's validated. And at this point, the client has the identity information for the user, so they can be considered authenticated. Now, tokens should be stored locally in app memory. It is recommended that we not store tokens in local storage because they're vulnerable there to cross-site scripting, and they're also accessible to any other app on the domain. When we make HTTP requests to our API, we're going to attach that access token in the authorization header. As we covered before, the API then validates the access token using middleware, and then data can be returned to our JavaScript application as JSON, which the application consumes. But in a single-page app, if we refresh the page, the entire single-page app reloads. And if we don't have user info or tokens in our app memory anymore, because we were told not to put them in local storage, then what we can do is use that authorization server cookie to check if the user's authorization server session is still valid. If it is, then the application can actually use an iframe and the authorization server cookie, and without prompting the user for their credentials again, it can silently request new tokens without user interaction. This is called silent authentication. However, a more recent challenge has come up, which is that browsers have implemented privacy measures, like Safari's intelligent tracking prevention, that block third-party cookies. And recall, this cookie is for the authorization server's domain, not the application's. So that means that ITP blocks silent authentication. And where does that leave us? It means that we're back to asking the user to re-authenticate every time they refresh the page or come back the next day, and this results in a less than ideal user experience. I'm sure folks have seen this before, where you log into an app and then you basically have to log in every single time you come back to the app. So there's an additional token type that I'll discuss to cover this, and that's refresh tokens. Now, refresh tokens are credentials used to obtain new tokens from the authorization server without making the user re-authenticate. The client is going to present the refresh token to the authorization server, and then the authorization server authenticates the client and validates the refresh token. At this point, if everything checks out, then the authorization server can issue new access and ID tokens. So historically, the problem with using refresh tokens in single-page applications is that they're very long-lived, and they can't be securely stored in the browser. I already talked about how we shouldn't put tokens in local storage. especially if they're long-lived. And the security risk of refresh token use in the browser just wasn't acceptable. So this is why we created silent authentication to manage this instead. However, in light especially of things like ITP and blocking third-party cookies, making silent authentication not really that feasible, authorization servers now support what we call refresh token rotation. And this enables single-page apps to use refresh tokens that are invalidated after a single use. So a new refresh token is issued each time a new access token is issued. And authorization servers have also built in automatic reuse detection, which reduces the threat surface and enables refresh tokens to be stored in the browser in local storage, unlike access and ID tokens, when used in conjunction with modern best practices for securing single-page apps. But why can't we just use cookies for single-page apps, similarly to how we use them for traditional server-side web apps? Well, cookies only work on the domain of the application. So if everything is on the same domain, then in fact cookies can work. Many single-page apps call APIs that live on other domains, though, and if they don't now, they may need to in the future. And if this is the case, then your domain session cookie won't work with the API's domain. But maybe this isn't a problem for you. Maybe you have a single-page app and a backend that are on the same domain. For example, maybe you have an Angular app that's running on a .NET background, or a React app that's running with a Node backend and API. And if you're only exposing your own API for the exclusive use of your own presentation layer or the single-page application, then cookies can actually work for this. It would look like this. You have your backend, which should be capable of executing code and also providing the API endpoints. The backend then serves the single-page application, which runs in the browser. And you have your authorization server. Then we can actually use backend routes to log the user in so that the backend application interacts with the authorization server to authenticate users. Then any data that's moving between the backend and the single-page app can be secured with an HTTP-only session cookie, which works because it's all on the same domain. However, maybe you can't do this. Maybe you need to scale. Maybe you have a JavaScript application that doesn't have a backend and it runs on serverless architecture. Or maybe you have APIs that live on other domains. And if this is the case, we do need to use tokens. So I'm going to talk about guidance for token use with JavaScript applications. The approach that we use for JavaScript apps is actually the same approach that's used in mobile applications, because mobile apps are also public clients. They're not capable of storing client secrets securely because they live on a user's device, not in a centralized, secure location. Remember, this is similar to the situation that we have with single-page apps because they're loaded into each user's browser. Now, this mobile and single-page application flow is called authorization code with proof key for code exchange, or PKCE for short. In this flow, the first thing we're going to do is exchange a code for a token. And we're going to do this sort of similarly to the way that we do with traditional web apps, but because this is a public client, we need to take some additional precautions. So let's take a look at how this actually works. Let's say we have our JavaScript app, and it's running in the user's browser, and then we have our authorization server. On the client side, we're going to create a random string, and this string is called a code verifier. Then we also have a hashing function, and the hashing function is called the code challenge method. Now, using this function, we'll hash the code verifier string to compute a hash string, which is called the code challenge. When a user comes along and they want to log in, we're going to take their authorization request and the code challenge method, and we're going to send all of these things to the authorization server's authorization endpoint. The authorization server then generates a code which is sent to the browser, and this code is received in a URL query string. And it can do this because interception of this code isn't dangerous. The code by itself doesn't grant access to anything. But once we have the code, then the code and the code verifier are sent to the authorization server's token endpoint. The authorization server then needs to confirm that the code it just received is the same one as the one the authorization server sent in response to the application's authorization request, the one that was delivered to the app in the query string. And it also has this code verifier, which is the original random string generated by the client. Now remember, we sent the code challenge, which was the hashed code verifier, and the code challenge method, which is the hashing method, from the application to the authorization server when we made that initial authorization request. The authorization server can now use the code challenge method to calculate or hash the code verifier to create the code challenge using the code verifier that it just received just now from this code exchange. The authorization server then compares its calculated code challenge to the code challenge that was sent by the application earlier. If these code challenges match, then tokens can be issued and they're delivered in a JSON object to the application. You probably see some similarities with this process as you did when I was describing the signature for JSON Web Tokens. In addition, we can also use refresh tokens with auth code with Pixie, as long as our authorization server supports refresh token rotation. But this is a ton of work, right? And a lot can potentially go wrong here. So similarly to how we would typically use a library to validate JSON Web Token signatures, we should really take advantage of SDKs or services to handle proof key for code exchange as well. We want to offload this type of thing to security and identity experts so that you can focus on building awesome applications in your core business. So I hope that this talk has demystified some of the standards and the basics of authorization and authentication, as well as how to implement them on the web. Now, identity itself is an enormous subject, right? We could talk for days and days about this. So to connect with me, if you want to learn more, I have a website and blog at maida.kim, and I've written several articles that cover these topics in depth, especially if you prefer written content to spoken for review. And then I also write about developer relations and career advancement. You can also connect with me on your preferred social platform by checking out this link. And you can grab these slides at this link in video format. So I've outputted them in video so that you can see all of the diagrams animating and things like that. So please come and talk to me if you want to chat, or if you just want stickers, that's also perfectly legit. And I really appreciate you giving me your time today. So thank you very much.
Thank you, Kim. All right, folks, we have about a 15-minute break. Up next on the Alpha stage is going to be Jimmy Bogard talking about fixing distributed systems fail. So stretch your legs, grab some coffee. We'll see you back here in 15.